We have a cantilever beam with a span of 1.6 meter and subjected to a point load at the tip of 7.2 kilonewtons. The beam is made out of a rectangular timber cross-section that has a width of 120 millimeters and a depth of 280 millimeters. And we are asked to determine the maximum horizontal shear stresses at points located 35 millimeters, 70 millimeters, 105 millimeters, and 140 millimeters below the top surface of the beam. In reality, what they are asking is the distribution of the shear stresses at the cross-section that has the shear force maximum, or the highest shear force in the beam. So the first thing that we are going to do then to determine what is the section that is critical in shear is draw the shear force diagram. So we calculate the reaction forces from equilibrium, and we have a fixed support that is going to develop a vertical reaction force that prevents translation at that point of 7.2 kilonewtons, and we have a bending moment, a reaction moment at the support as well of 11.52 kilonewtons meter, and that moment is going to cause compression at the bottom of the beam and tension at the top of the beam. So once that we have the external reactions as well as the applied load, we can proceed to draw the shear force diagram, and then from the shear force diagram the bending moment diagram. And we observe from the shear force diagram that the beam is subjected to a constant shear force of 7.2 kilonewtons. So we can assure that the maximum shear force is that value, 7.2 kilonewtons. Note that the entire beam is subjected to the same shear force, so every cross-section along the span of the beam will be subjected to the same distribution of shear stresses. Okay, so once that we have that identified that maximum shear force, we can proceed to calculate the distribution of shear stresses along the depth of the cross-section, and we are going to do that through the shear formula. The shear formula is telling us that the shear stress tau is equal to the shear force V, the first moment of area of the area above or below the level where we are calculating those shear stresses, and divided by the moment of inertia with respect to the bending axis or neutral axis, and B represents the width over which the shear stresses are distributed. So for the problem at hand, we have that the shear force is the maximum shear force of 7.2 kilonewtons. The first moment of area will depend on which point we are calculating the shear stress. Remember, we were asked to determine the shear stresses at 35 millimeters below the surface, 70 millimeters below the surface, 105 millimeters below the surface, and 140 millimeters below the surface. So the first moment of area will differ depending on where we are calculating the stresses, but the way we calculate that first moment of area is just the area above or below that level where we are calculating the stresses times the distance of the centroid of that area to the neutral axis. The moment of inertia with respect to the bending axis here is the BH cube over 12. We have a rectangular cross section. The B would be the dimension parallel to the bending axis. In this case, the bending axis is the Z axis, and H is the dimension perpendicular to that axis. So we substitute the values and we find that this cross section has a moment of inertia of 219 million millimeters to the fourth. And finally, B, the width over which the shear stresses are distributed, is 120 millimeters. So then let's proceed to calculate the shear stresses at each level as we were asked in the problem statement. And what I'm going to do is set up a table. So we have on the first column the distances from the top of the beam that we were asked to calculate the shear stresses. And then the second column is Y. Note that the neutral axis is located always at the centroidal axis, so it's 140 millimeters from either the top or the bottom. And Y is the distance from that neutral axis. So if I have 35 millimeters measured from the top, Y would be then 140 minus 35, 105. and we calculate the values of y for the other levels as well. Now, the first moment of area, which was given by equation 2 previously, I told you that is the area at the level that we are calculating the shear stresses, so it's the area above or below that level times the distance of the centroid of that area to the neutral axis. So let's look, for instance, the case where we are calculating shear stresses at 35 millimeters from the top. So we have that area, and what we need to calculate for the first moment of area is that particular area that is highlighted in red. So it would be the depth 35 times the width 120, and then the distance of the centroid of that area to the neutral axis. So note that y is 105, and then the centroid is 35 over 2. So we end up with the distance 122.5, which is the 105 plus 17.5. We substitute the values of the V, the Q that we just calculated, and divided by the product of the moment of inertia and B that we had previously, and we find that at that level the shear stress is 141 kilopascals. You have to be careful with the units. So in the shear formula you have, if you have V as kilonewtons, and then you want to have kilopascals at the end, it would have to be kilonewtons per meter square. So everything else that is in meters or millimeters would have to be converted into meters. If you are using V in newtons and you put the other dimensions that have distance dimensions as millimeters, you would end up with newtons millimeter square, which is megapascals. So you would have obtained 0.141 megapascals. If it's a very small number, you can just convert it to the next lower level of the unit. So in this case, the stress level at 35 millimeters from the top or 105 millimeters from the neutral axis is 141 kilopascals. And we proceed the same for each of the levels. So we go now to 70 millimeters below the surface, is 70 millimeters from the neutral axis. So again, you see the area highlighted in red. So the area would be 70 times 120, and then we have to multiply with the distance of the centroid of that area to the neutral axis, which is 105. So it would be the 70 plus 70 divided by 2, so 70 plus 35. That's where the 105 comes, and that's the first moment of area for the area above the level where we are calculating the shear stresses. We substitute into the shear formula, and we find that the stress level at that point is 241 kilopascals. We proceed to the next level, 105 millimeters from the top. Again, you see the area highlighted in red. So now the first moment of area would be 105 times 120. The 105 comes from 140, which is half of the height of the cross section, minus the 35 millimeters of y. And then we have to multiply that by the distance of the centroid of that area to the neutral axis, which is 35 plus the 105 divided by 2, which is the 87.5. Plugging into the shear formula, and you find out that is 301 kilopascals. And we do exactly the same thing for 140 millimeters below the surface, below the top surface. That corresponds to half of the cross section, because basically what they are asking us to calculate is the shear stress at the neutral axis. So the first moment of area is that area. It would be 140 times 120. And then the distance of the centroid of that area to the neutral axis is 70. Plugging into the shear formula, and we find that the corresponding shear stress is 321 kilopascals. Note that the distribution of the stresses below the neutral axis will follow, because this is a cross-section that is symmetric with respect to the neutral axis. But I want you to note is the distribution of the shear stresses follows a parabolic distribution with zero values at the top and bottom fibers and the maximum value at the neutral axis. So always remember that the shear formula, where we have the VQ over IB, V over IB is going to be constant for the cross-section, so the only thing that varies within the cross-section is Q, and Q has a parabolic distribution along the depth. with a zero value at the top and at the bottom, and maximum at the neutral axis. So whenever you have a cross section, we know the neutral axis coincides with the centroidal axis, and at that level the shear stress is always going to be maximum.